Hello, I wanted to take some time to now go over the quantum numbers worksheet with you and talk a little bit more in detail about the ins and outs of quantum numbers. So the first thing we have here, state the four quantum numbers and the possible values that they may have. And I went over this in my earlier video, but just to review, our four quantum numbers, we have n, which is the principal quantum number. And it can be any whole number. So 1, 2, 3, and so on. Okay. Then we have L, which remember is our azimuthal or our angular momentum, and it is equal to n minus 1. So it can be 0, 1, 2, 3, so on and so on, but it has to be n minus 1. So whatever n is, we subtract 1, and that gives us L. M sub L, remember, is the exact orbital where our electron can be found. And so M sub L is equal to negative L to positive L. So if L is 1, then we can have negative 1, 0, positive 1. So we can have negative numbers all the way into positive numbers. And then for M sub S, remember there's only two possible values, positive 1/2 and negative 1/2. So now if we look at the second question here, we're given some quantum numbers and we want to identify those orbitals, okay? So we have n equals 3 and L equals 0. So because we have n equals 3, then we know that the orbital is going to be in the third level. L equals 0 always refers to an s orbital. It doesn't matter what the n value is. If we have an L value of 0, then that equals s. If we look at B here, we see that n is equal to 3. So again, we're going to have a 3. And this time L is equal to 1. Anytime we have an L value of 1, that indicates a p orbital. If we look at C, we still see an n value of 3, but this time an L value of 2. 2 refers to D. So an L value of 2 refers to a D orbital. And then we look at D, we see n is equal to 5 and L is equal to 0. Just like in part A where we had an L value of 0, this also indicates an s orbital. Now in number 3, we're going to do the opposite. Okay, we're given the n and L values or we're given the orbitals and we need to find the n and L values. So n is just going to be equal to the number that's here. So for A, n would be equal to 1. And then our L is going to correspond to the letter here. Remember that if we have an S, L is always 0. Okay. So in B, our n is going to be 3. We see S here again, so L again is 0. For C, n is going to equal to 2 because that's the number we see there. And this time we have P, so L is going to equal 1. And then in part D, we have n equal to 4, L equal to 2. And then we move up 1 on E, n equal to 5, and this time L is equal to 3. Okay, so just keep in mind that an S corresponds to an L equal to 0. P corresponds to an L value of 1. D corresponds to an L value of 2. And F corresponds to an L value of 3. So if we turn over here and look at the back of this, if we look at the first one here, let me get it adjusted for you. All right, so if we look at the first one, we are looking at orbital destinations that are theoretically possible. So what we've got here are N and L. And remember that L is equal to N minus 1. So our L value, okay, and whatever orbital that corresponds to, has to be 1 less than what our N is. So if we look at A, we see 7s. Well, we know that that would be an N equals 7 and L equals 0. That's acceptable. That is a possible orbital destination because our L value is 6 or below, which is what's acceptable. If we look at B, our N is 1, P is 1, or our L is 1 because of the P. That's not possible because our N value and our L value can't be the same. So B would not be theoretically possible. Okay, so you need to finish 4 on your own. If we look at 5, the maximum number of electrons that can occupy a particular orbital. So an s orbital, a spherical orbital, can only hold 2 electrons. It only has one space, one orbital available. So it only has one orbital. When we look at P, okay, P actually has 3 orbitals, and according to Pauli exclusion principle, 2 electrons can fit in each orbital, so we say 3 times 2, that gives us 6. D, there are 5 D orbitals, and we say 5 times 2, we have possibility of 10 electrons there. If we look at F, F has 7 orbitals, so we know that that has to be 14. And then we look at G. G has 9 possible orbitals, and we multiply that by 2 to get 18. Now, because of the Pauli exclusion principle, okay, 2 things happen. Number 1, that no 2 electrons can have the same set of quantum numbers, which means that each orbital can only hold 2 electrons, as we just saw in number 5. So that means that with the S having a maximum number of electrons of 2, and then P of 6 and D of 10, that some electron configurations that we're going to see here, 4, 6, and 7, are not possible because they violate the Pauli exclusion principle. So if we look at 6A, you see here, and this is read as 1s2, 2s2, 2p7. Okay? This is ruled out. This is not valid. It's ruled out because we have that p7 right there. We already said for number 5 that the p orbitals could only hold 6 electrons. So this is not valid because of the p7 there. Okay? And you need to finish 6 on your own. Now we'll look at 7. So if we look at number 7, in this circumstance, we need to explain why these aren't possible. So if we look at 1, or look at A here, we have 1s2, 2s3, 2p3. Well, this is not valid because S can only have a maximum of 2 electrons. And we've got an S with a 3 there. Okay? So that's not possible. If we look at B here, there's actually a couple of things wrong with B. Notice we have 2p3, 3s6. Well, the first thing we recognize is that S can only hold a max of 2 electrons, so that's wrong. But P isn't full, and we've moved on to something else. We've moved on to the next level. So, according to Pauli exclusion principle, according to Hund's rule, the P must fill before we move on. So the P has to be full before we can go to another level. So we have to do things we have to assign electrons in a particular order. We can't go out of order. So you need to finish C and D on your own.